Hi there, it's Manuel. Today I want to talk about growth solvers. Growth solvers are quite common these days, and we did tutorials on growth solvers already, but usually you don't get directions from growth solvers. What if you want to grow feathers on a surface or knit loops that have a direction to them? Then you will find this neat little trick I show you today quite handy, because I will use a gradient to generate directions on the surface of an object. So I will create a vector field that is parameterizing the surface. So let's directly dive into Houdini and get started. First lay down a geo node and call it growth. Then dive inside. We'll use the file node that you find inside to import the geo I provide beneath this video. As usually, I did this geo in 3D code, so it's far too big. So append a transform and scale it down by a factor of 100, so 0.01, like so. That's a more reasonable size. Today I want to do something a little different than before. I don't want to do a growth solver with proximity on a point cloud, but I want to do a mesh-based growth solver that uses the neighbors of the mesh points. For this I need a clean mesh, and this mesh here that comes in from 3D code is not clean at all. So let's append a remesh. As soon as the remesh is appended, the result is immediately far more clean. By upping the iterations to 2, we can enhance the result, but then we have to dial down the target edge length to make the polys smaller. So maybe let's use 0.03 or something. That gives a nice mesh distribution like so. The next thing is that I want to use one point to start the growth. So just append a group node. And we want to group exactly one point, and we couldn't do that by just typing the point number here in base group. Let's say use point number 3. Set the group to points and call the group seeds. I use the plural because we can use more than just one point. Where is the selected point? Let's have a look. Do you find it? Here it is. It's here right in the center. Now that we have this one point, it's time to set the values, the initial values for our growth solver. So let's append a wrangle, a point wrangle. This will be used to set the initial value. Let's call this set initial values. And I want this to operate on the seeds group only, because I want to set the value for the infection to 0 for all the points but this one here. So if I now write here add infect, that is my infection attribute. You can call it however you like, but I will call it infect, is 1. Now I set this value here to only this one point. But the attribute is created at the same time, and thus all the other points get the default value, and because I did not specify a default value, they get the default value of 0. We can check this in the geometry spreadsheet. Here you have the infection value of 0 on all the points but point number 3, which has infection value of 1. That's great. So our infection will start here with an infection value of 1, and then it will propagate over the surface of the object. A growth solver works by looking up the neighbors of every point and then accumulating this infection attribute. So a very vital part of the algorithm is to find the neighbors. That means for every point in every iteration, all the neighbors have to be found, and that is quite a costly operation. That's why I decided to pre-compute the neighbors and save them as an attribute, because then I can just look up the attribute instead of recomputing the neighbors in every step. So let's do that. Let's append another wrangle, point wrangle again. And let's call this find neighbors. Okay. Now make the wrangle active and press Alt-E to open the code editor. And here we will do something handy. We want to find the neighbors and store them to an array attribute. Why an array attribute? Because the points have different amount of neighbors. Some points will have 3 neighbors, some points will have 5 neighbors. We cannot know beforehand. So let's use an attribute, because then we can store as many neighbors as we find. So let's create a new variable of type integer, int, and then neighbors. And to indicate that this should be an array, we use brackets, rectangular brackets. And then we invoke the vex function to find the neighbors, so neighbors. And then the standard brackets. Don't forget the semicolon at the end. We want to look them up in geometry stream 0. So the first port, and then we want the neighbors for the current point, and the current point has the number pt num. So don't get confused, because I use the exactly same name for the variable as for the function, but that is just because I decided to do it that way. You can name it however you like. You can name it James or something, but I use neighbors because it's descriptive. And then I invoke the vex function that looks up this point and writes all the IDs of the neighboring points into this array. And now in a second step, I want to set the information from this array to an attribute. So it's an integer attribute. We have to state this, and now the brackets will be directly after the I for integer, because this is attribute syntax. Now an @ symbol, and now neighbors. So here is neighbors again, but this time it's referring to the attribute. So we have 3 neighbors here: the function, a variable, and the attribute. And we want to set this attribute to the contents of neighbors, like so. Press apply and accept. This is a little bit convoluted, maybe, but I think it's easier to read. Of course, you could assign this function or the returns of this function here directly to the attribute. Using this intermediate variable is not necessary. It's just that me personally, I think it's easier to read, and I have the opportunity to do something to the result if I want to later. That's why I developed the habit of doing it like this. If you now have a look at the geometry spreadsheet, you see that we have a neighbor attribute, and it's an array indicated by these brackets. And in these arrays that every point now carries, we have the indices of the neighboring points. So in this very first case, 16, 3, 2, 1, etc. And these arrays are of different lengths because every point has a different amount of neighbors. But it's a very great thing, because now we have a speed advantage at the cost of using more memory. Now that we have the neighbors, let's put down a solver, because it's about making stuff grow. That can be done with a solver. And dive inside. Inside you find these 5 nodes here, the 4 inputs and the previous frame. Append a point wrangle to the previous frame node and make it visible. And now press Alt-E and let's write the solver. The very first thing we want to do is to look up the neighbors we just stored. So let's again create a variable, this time integer. Let's again call it neighbors. And we need square brackets again to indicate this is an array. And we want to read the array attribute neighbors. So it's exactly the reverse of the process we did a second ago. Then we will need a float variable. I call it accum for accumulation, and we initialize it with 0, and then we need a second variable, float infect, because we plan on reading the infection value from the points, and we initialize this one with 0, 2, like so. Great, now we have a neighbors array with all the neighbors, and we want to run over all the neighbors and add the infection values together. So let's create a for each loop for this. For each. And now we have to state the runtime variable, which is point. So the currently processed point will be stored in this variable point, and it should run over the array neighbours. So let's tell it to run over neighbours, and then we need curly brackets, open, close, like so. Now everything that is inside of this block will be executed for all the neighboring points. First, let's look up the infection value. So in fact, I don't have to declare this variable because I declared it in front of the loop. So in fact is, and let's use a point function. On geometry stream 0, we want to look up the attribute called infect. And we want to do this for the point with number point. So for the currently processed point. Good, now we have the infection value. I could start to accumulate these infection values directly, but then the infection values really go through the ceiling very, very quickly. So I will do something a little different. I want to check if the infection value is not 0. So if infect is greater than 0, then and only then do something. Like so. And in this case, add something to the accum variable, plus equals, let's say 0.1. So instead of using the infection value directly, I just increase the accumulation variable by 0.1 every time a point is found that has an infection value greater than 0. This comes in handy because then the values don't increase so quickly, but more linearly. Once the loop has finished doing its thing, we will have an accumulated value inside of the variable accum. Time to set it to the infection value. So add infect will be infect plus accum, and then divided by the length of the neighbors array. Len neighbors. Because I want to find the average basically. So I add up 0.1 for every neighbor that has an infection value bigger than 0, so that is infected, and then I divide them, or I divide the sum by the count of neighbors to form an average basically. That is all there is to it. So press apply and accept. Go one level up, make the solver visible, and let's look at the geometry spreadsheet to see if something happens, and yes, the infection values are counting up. We can make this visible by using a visualizer. So append visualize, and this should visualize the infect attribute, like so. And let's say ramped attribute, and the min and max will be 0 and 1. And you see it's very quick, but yeah, now the infection spreads and covers sooner or later the entire object, as you can see here. Because now for every neighbor that is infected, a value is added, and thus the infection grows over the surface quickly. Okay, now I have a value here on my object that is increasing. At the moment everything is red, but that is only due to the settings of this visualizer. If I increase the max, let's increase it quite a bit, 20 let's say, you see that this is actually a value gradient. So the values are higher and higher the older the point is basically. So where the infection started, the values are the highest, and the new points have lower values. A gradient. And we can use the mathematical construct that is called gradient to turn this information into vectors. Fortunately, Houdini has a node that does this for us. It's called the polyframe node that is used to give tangent information and framing to curves and surfaces. But it can calculate the gradient from an attribute too. If we set it to style attribute gradient, and now we can give it an attribute name, for example, our infect and it will find the gradient. The gradient is the vector that points to the direction of the biggest increase of the function. So in our case, it points along this color gradient here, which is exactly the direction we want. There is only one problem, and the problem is that the polyframe does not operate on float attributes. It operates on vectors. So we have to first turn our float attribute in fact into a vector. Let's do that. Let's append a wrangle, point wrangle here, and let's state v for vector. Let's call the new attribute grad or temp, it really doesn't matter too much, and set this vector to add in fact, because that is the attribute we want to use for our calculation, and then 0 and 0. The polyframe node is designed to find the attribute gradient from UVs on vertex level, and that is why it uses vectors and the first and second component of vectors. So to trick it into using our attribute, we do this. Call this wrangle set grad from in fact or something, and append it to the polyframe. And now we have to give polyframe the grad attribute. This now generates tangents and normals. We don't need the normals, so check them off. And the tangents should be here. If we hide all attributes and just visualize the tangents, we don't find them, and that is because they are here on vertex level. That's the second specialty of polyframe. It's operating on vertex level. Again, this is because it's designed to work on UVs. So we have tangents on vertex level. Let's visualize them. This time using a visualizer here from the menu. Let's add a new marker. The class is vertex, and tangent is what we want to visualize. It's a vector. And here's our gradient. Look at this, isn't this beautiful? Let's make the vectors a little smaller. And you see how beautiful this is. This is our growth direction. If you look closer, you see that it's calculating the vectors per vertex, and the vectors have different directions per each vertex. That's due to the fact that it's taking the polygonal structure into account, and the value is increasing for every vertex differently. But overall, it gives us exactly the vector field we are after. To use this on points, we can simply promote it to point level. So let's promote the attribute called tangent from vertex to point level. Let's reflect this change here in the visualizer now that it's on point level. And here we have the average vector from the vertices. And this is our beautiful vector field that we can use to create the orientation. So let's build the orient attribute. For this I use a VOP, this time a point VOP. Call it build orient, and we will use a double cross product to build the orient from this tangent vector and the normal. So first we need the tangent vector, so bind it. It will be a vector called tangent, like so, and then lay down a cross product. And we will cross the tangent with a normal. So normal cross tangent. This gives us a vector that is orthogonal to both of them. And then a second cross product. And this time I will cross a tangent with the vector I just created, giving me a new normal, so to speak. And now I need a vector to matrix. A vector to matrix 3. And the vector that we computed here will be the y-axis, because it's the normal. The tangent should be my z-axis, and this vector here is my x-axis. Now that I have a matrix 3, I can easily convert this to a quaternion with matrix to quaternion. matrix 3 to quaternion. And I can use this quaternion to store it with a bind export to the orient attribute. That is by default a vector 4 quaternion, indicated by this light yellow color here. Now we have an orient attribute on our geometry. And now that we have that, we can put down a copy to points and maybe create a tube to have a directional geometry and copy this to the surface. And we need a transform to make the tube smaller, 0.01, and maybe let's make the tube a little longer, height 2, and turn off show guide geometry here on the copy to points and turn off the visualizer. But the tube is not oriented correctly, so let's orient it along the z-axis, maybe make it bigger again, 4, and transform it to make it even smaller, like so. Well, like so. And you see now the tubes follow beautifully the vector field we just created. And that holds true not only for the tube, but for every object you want to copy onto the surface, be it a feather or a knit loop or whatever. So this gives us orientations that follow the growth direction of our growth solver. So the very last step might be that we want to remove all the points that are not infected yet. We can do this by using a group expression. And let's group all the points. This should be group type points. Let's call the group keep. And let's keep all the points where the infect value is bigger than 0. Thus keeping all the points that are infected. And if we now append a blast, we can delete everything that is not infected by using the keep group here, deleting non-selected, and now we have a growing set of points, as you can see here. If we now use this to copy the stuff, it not only uses a direction, but it grows at the same time beautifully. And this is how you can easily find the direction of your growth solver and a method for creating a vector field on the surface of an object that beautifully flows over the surface, as you can see here. I hope you liked this trick, and see you next time. And I want to say a very big thank you to all our patrons, especially Mohammed Al-Abri, Chris Hebert, Nick, Bahaman Jahan Bakshi, John Kuntz, and Joseph Howerton. Thanks a lot.